Okay, so curve sketching. So what you want to be able to do is you want to take really any type of curve, and you want to be able to sketch a graph of it. And these are the guidelines, and this is what you're going to be asked to do on your test as well. And I will lay out for you the guidelines that you need to have, but this is what we want to be able to do. We want to be able to understand all these different pieces within a curve. Now, back in pre-calculus, you guys could do amazing things like find all of the intercepts. Well, we know a lot more than that now. We know how to find the intercepts. We know how to find the maximums, the minimums. We know how to find where it's increasing, decreasing. We know how to find concavity, asymptotes. There's a lot more stuff that we can do. So we want to put this all together to be able to actually find a graph of the curve. Domain. What does domain represent? Domain is all the possible x values that we can input. As you think about domain, think about this, okay? For polynomials, domain is all real numbers, okay? So if you're given a polynomial, domains can be all real numbers. But if you're given a rational expression, let's think about domain for something like, say, 1 over x minus 2. What would the domain be there? All real numbers except for 2. So you would say x not equal to 2. So there's where we want to think about those pieces, okay? So for domain, that's kind of where we're going to move our brain. Now, there's a lot of different graphs that we can look at. We could talk about cosecant. We could talk about fractional exponents. But we're going to really isolate it to nicer functions that we've seen before. We're not going to cover all of them. We just don't have that time. Range, I'll get to that later. But intercepts, okay? That's where we solve f of x equal to 0. That's for your x-intercepts. To find the y-intercept, we set x equal to 0, and we solve. So x and y-intercepts are something that you've practiced before in other classes we should be able to find. Symmetrical. I'm going to give you some examples of graphs or symmetry. We won't go over all the symmetry tests, but I'll give you some examples. Y equals x squared. That's symmetrical about the y-axis, right? Okay. Y equals x to the third. That's symmetrical about the origin. You have all sorts of examples here that work out for symmetry. So these do have symmetry in certain ways. Those are things we're going to keep in mind. I won't ask you to necessarily identify symmetry, but it's something that can be helpful. Asymptotes. Now, asymptotes happen at interesting places. First of all, asymptotes are going to occur where the function is undefined. For example, here, 1 over x minus 2, you have a vertical asymptote that will run at positive 2. Yeah, asymptote is the only word I knew until I came here and I heard people pronouncing asymptote. And if you if you look in the dictionary, it allows both pronunciations. So, well, I was wondering. I was like, I was wondering if I said it wrong this whole time, but I found more people actually say asymptote. But in my circle, I've never heard asymptote. It's because I went to a weird college. Only the best. Only the best. Who from last year went to St. Olaf? Did anybody from last year go to St. Olaf? Who? Brooke went to Carleton. Okay. All right. The other asymptotes that we can have are horizontal asymptotes. And horizontal asymptotes occur as we find the limit of f of x as x approaches positive and negative infinity. So yesterday, when you guys were finding the limits of all those functions, they approach positive or negative infinity, those represent the types of horizontal asymptotes. That's what the function slowly approaches as it goes on towards infinity. Now, they don't always have horizontal asymptotes, but some of them do. Okay, now let's get to the calculus piece. Intervals for increasing and decreasing. What tells us intervals for increasing and decreasing? Or I'm sorry, we should just write f prime of x is greater than 0. Function is increasing. If f prime of x is less than 0, the function is decreasing. So this is really a nice review of a lot of pieces that we've covered, as you can see, which is why it's a great section. They're all great sections. It's like, which one could you really leave out? Local maxes and mins. That's where f prime of x is equal to 0. When the derivative is equal to 0, we find that we have a local max and local min, as long as it's differentiable at that point. Concavity is double prime. If f double prime of x is greater than 0 or positive, then it's concave up. If f double prime of x is less than 0, then it's concave down. And if f double prime of x is equal to 0, what do we have? Oh, no. Some kind of point. Starts with an I, reminds with inflection. Point of inflection. Can't forget about that. And so we can also use this concavity to just finish off our notes here real quick. We'll use our concavity to tell us something about a max and a min. Real quick, if we have a max, is it concave up or concave down? If you have a max, is it concave up or concave down? Down. So for a max, f double prime of x is negative. And if you have a minimum, is that concave up or down? Concave up. So f double prime of x would be positive. And so that really gives us a good idea of all the interesting pieces about a function that we would want to know in order to graph it. Now, try to just put yourself back a couple hundred years right now. You don't have a calculator. You can't press graph. And you have a couple options. You can either plug in a bunch of points and start to plot dots on a sheet of paper, or you could do this stuff to generate what your graph looks like. You're gonna you're gonna do this stuff because it's gonna be much more accurate and it's gonna be a lot quicker. So let's look at a basic example. F of x equals x to the third minus 2x squared minus 3x. Okay? Anybody first tell me, what's the domain of that function? All real numbers. We'll get to the range in a second, but I would like to find the intercepts. The y-intercept is generally the easiest one to find. The way I find the y-intercept is I plug in 0 for x. If you plug in 0 for x, what does y end up to be? 0. So intercept, y-intercept is 0. In order to figure out the x-intercepts, I set the function equal to 0. So I'm going to use my space down here. I'm going to say 0 is equal to x to the third minus 2x squared minus 3x. What do? Factor out an x. Very good. 0 equals x times x squared minus 2x minus 3. Now what? X minus 3 x plus 1. So that means I have zeros at 0, 3, negative 1. So intercepts, x-intercept would be at 0, 3, and negative 1. So I have something to go off. And if you remember last year during pre-calculus, you would now sketch it through those points. But you always said, well, how high do I draw it, or how low do I draw it? Well, now we get to find that out by looking at intervals of increasing and decreasing and so on and so forth. This doesn't happen to have symmetry. We're gonna leave that alone. But asymptotes. Let's think about it for a second. The limit of this function as x approaches positive infinity. Okay, if you plug in positive infinity in this thing, do you know what you're gonna get? You're gonna get a huge number. And this x to the third is going to dominate the function, okay? You're going to get infinity to the third power, which is going to make a very, very large positive number. So the limit as x approaches infinity of f of x is going to be infinity. So you don't have a horizontal asymptote that it approaches. Now, if you try the limit as x approaches negative infinity of f of x, if we plugged in a negative number and took it to the third power, would we get a positive or a negative? A negative. Notice I'm only looking at this front term. X to the third is what drives the function. The rest of it, it doesn't play any role at all by the time you cube it. Squaring it, multiplying by 3 has no effect on it once you cube it. So we are going to get negative infinity there. So in effect, you can see that your range would be from negative infinity to positive infinity as well. So negative infinity and positive infinity are all real numbers. So this does not have horizontal asymptotes. It doesn't have end behavior that we could just follow along with. It approaches infinity, okay? Yeah, well, let's say that it approached 1, then, the graph would maybe look something like that. But because this thing, when you plug in big numbers here, you're just going to continue to get really, really huge numbers. And if you think about a cubic function, if you think about the nature of it, it's going to look something like this, right? It just heads off towards infinity. That's all it does. So it doesn't have any behavior, doesn't have anything we could kind of follow along with and graph. It just continues to go on. So we just leave it. Now the example on the back side is just slightly different. So that'll give you a little bit different example. So intervals of increasing and decreasing. What do I have to do to figure those out? Derivative. Nice job. F prime of x. Whoop. I should write that down where I have some more space and write my answer there. So we'll do it right here. F prime of x is equal to what? 3x squared minus 4x minus 3. Okay? Now, in order to find intervals of increasing and decreasing, that's where it changes from positive to negative. So I should really find out where this thing's equal to 0 at. How do I figure out where this is equal to 0? Unfortunately, I don't think that this thing factors. Can somebody plug in their quadratic formula on their calculator and come up with a couple decimals for me? Negative 0.54 and 1.868. So 1.87 we'll say. So it appears that those are the spots where it changes from increasing to decreasing. What happens at these points? Local max and local min. changes from increasing to decreasing, but this is one example, okay? So I'm going to have a few intervals here, okay? I'm going to have a few intervals here. One interval is going to be from negative infinity to negative 0.54. Another interval is going to be from negative 0.54 to 1.87. And another interval will be from 1.87 to positive infinity. And the question is, are these intervals of increasing or decreasing? It will be intervals of increasing if a number within this range right here, within this interval, when I plug it into the derivative, I get a positive. So what number would you like to plug in here? Negative 1. So 3 times negative 1 squared would be positive 3 plus 4 minus 3 gives you 4. So this is positive. So it's increasing there. Now I plug in, let's plug in 0 even. 0 is a really good one, isn't it? If you plug in 0, you get negative 3, so it's negative here. And we plug in 2 for the last one. 2 squared is 4 times 3 is 12. Minus 8 minus 3 is positive 1, so it's positive. So positive, negative, positive. So I do have my intervals of increasing or decreasing. I'm going to write increasing for negative infinity to negative 0.54. And from 1.87 to infinity. If I have what? We're going to use this to sketch the graph. Yeah. Right. Decreasing from negative 0.54 to, whoop, to 1.87. We are going to have local maxes or mins, but first let's figure out concavity. Before we do local max and mins, let's do concavity. How do I figure out concavity? To figure out concavity, I have to find the f double prime. Very good. F double prime of x is equal to 6x minus 4. Set it equal to 0. That will be your point of inflection. 0 equals 6x minus 4. Add the 4, divide by the 6. X is equal to 2/3. So now I have two regions of concavity. I have concavity from negative infinity to 2/3. And from 2/3 to positive infinity. And we want to figure out where it's concave up and concave down. What number would you like to plug in between negative infinity and 2/3? 0. So I plug it into my second derivative. 0 minus 4 is negative 4. Negative. So it looks like it's concave down right here. And if we plug in 1, we get positive 2. So it's positive there, so it's concave up there. So I've tested my increasing and decreasing. I've tested my concavity. So let's give it a shot here. Local maxes and mins. First we'll do concavity. I'm going to say concave up from 2/3 to infinity. And I'm going to say concave down from negative infinity to 2/3. So we're almost done here, but I do have something else I need to do before I sketch the graph, and that's I need to really think about the maxes and the mins. I have two interesting points. One would be at negative 0.54, and the other one would be at 1.87. Okay? Yep. Now, let's figure out what happens there, okay? Is negative 0.54 in the region of concave up or concave down? It's in the region of concave down. So therefore, is it a max or a min? Max. 1.87, is that in the region of concave up or concave down? It's in the region of concave up. So therefore, it is a min. I would like to know how high or low it goes. How do I figure that out? Plug these points back into the original function. So if I type it in, y equals x to the third minus 2x squared minus 3x, and I go to my table and I type in negative 0.54, I get 0.879. So 0.88. And if I type in 1.87, I get negative 0.606 or negative 0.61. Oh, what did I? Negative 6.07. We're ready to sketch the graph. As you look at my x values, I need to plot from negative 3 to positive 3. I have zeros at negative 1, at 0, and at positive 3. Those are points that my graph goes through. For my y values, it looks like if I go to a max value of 0.88 and a minimum of negative 6. So if I made this into eighths, I would be okay. So I'll go 8, 4, I'm dividing up my axis so I get a nice graph here. I know because I had my minimum value is a negative 6 and my maximum value is a positive 0.9 for my local spots. So that's going to give me a good place to draw my graph. So let's plot those. I have negative 0.54 and 0.88. So negative 0.54 and 0.88 will be right there. And then 1.87, so right about here, and negative 6, approximately, right there. And now we're able to sketch our graph. Well, let's check that out, okay? We've got my window from negative 3 to 3 and negative 8 to 8. If I graph that, it just humor me for a second. Doesn't that look identical to that? Yeah, and you're more like this. So if I draw this, look at that. I mean, that's absurd how similar it is. What do you? Then you don't belong in this class. I mean, look at it. That's this. I did that. Yeah, we did that. Hey, you guys, we're not gonna use the rest of this time real wisely if I give you work time. So let's try to finish off some of the seconds so you can have time. Otherwise, tomorrow we gotta do the second. So let's try to finish off the back. Okay. So that you should love that. That's great. Okay, domain. Somebody tell me. Very good. X not equal to -2. Range, we'll check it out in a little bit. Intercepts. To figure out the y-intercept, I plug in 0 for x. If you plug in 0 for x, you get 0 over 2, which is 0. So the y-intercept, y-intercept is equal to 0. How do I find the x-intercept? I set the function equal to 0. So 0 equals 3x over x plus 2. I'm going to cross multiply and solve. 3x equals 0. X is 0. So it looks like it passes right through the origin. What? Okay. So x-intercept, 0. What? Yeah. Asymptotes. A little bit more interesting. A little bit more interesting. Limit as x goes to infinity of f of x. Let's think about this. As you approach infinity, 3x over x plus 2. Anybody want to guess what the limit is? It is 3. 3x over x plus 2, we would divide the top and bottom both by x. So that would be 3 over 1 plus 2 over x. That goes to 0. You're left with 3 over 1, which is 3. Okay? Yep. So you can tell here that I have a horizontal asymptote of x is equal, or I'm sorry, y is equal to 3. Asymptote, y equals 3. I have a vertical asymptote. Anybody want to guess what it is? What's that? Horizontal asymptote. End behavior, limit as x approaches infinity. So as you approach infinity, as you're going that way, horizontal asymptote. -2 would be our point where it's undefined. Intervals of increasing and decreasing. This is where it's kind of interesting here. We need to take the first derivative and the second derivative. What is the derivative of this function? F prime of x is equal to, how do I find the derivative? 3x over x plus 2. Quotient rule. Derivative of the top is 3 minus, times the bottom, which is x plus 2 minus 3x times 1. All over what? X plus 2 quantity squared. Beautiful. And so I end up with f prime of x is equal to this is interesting. Very interesting. What are my critical points? Can this ever be equal to 0? No, the numerator can never be equal to 0. Where is it undefined? -2. So -2 is my only critical point here. So here's my intervals of increasing or decreasing. -infinity to -2, and -2 to positive infinity. Those are my intervals of increasing or decreasing. What number in -infinity and -2 would you like to plug in? -3? So -3 plus 2 squared is 1. 6 divided by 1 is, so it's positive, right? So it looks like it's increasing. There. Now what number would you like to plug in? Okay, we plug in 0, we get positive. That tells us that it's increasing. So, is it ever decreasing? No. So the behavior of this is increasing from the intervals negative infinity to negative 2 and negative 2 to positive infinity. Is the derivative ever equal to 0? No. So do you have any local maxes or mins? None. Before we only have concavity. We're running out of time, so I just want to finish this off so you can see. I want to sketch my asymptotes. We know it passes through here, and we also know that we have asymptotes at y equals 3, 1, 2, 3, and x equals negative 2. Now, if we tested this, what you would find is that it's concave up over here. It's concave up, and it has to follow the asymptotes. Concave up. And if you tested it over in this region, you would find that it is, in fact, concave down. And so it passes through 0, 0 like that and follows that region there. Concave up, concave down. Any inflection point? No. Where does it change inflection, though? Or where does it change concavity? At the critical point of negative 2. Those are the kind of examples, say 4 or 5 problems that we want to work on tomorrow in our assignment. So that's what we're going to work on. The range would be from negative infinity to positive infinity, excluding the value of 3. Range goes from here to here. The only value it doesn't include is positive 3.